typically speaking, we talked about how simple random samples are sort of the gold standard for picking people to be in your sample, or in an experiment, for example, you would want to, when you go to you basically go to decide who gets what treatment, then you always want to implement simple random sampling in there. And so like in the one, we were talking about the one with people with folic acid or placebos. So in a completely randomized design, you just take the people you start with, and then you use a simple random sample to pick out half of them. So essentially, 2,250 would go there, and then the other ones, just by default, would go there. And then like one group would get the treatment, one group would get the control, or if there was other factors, they might split within or something like that. But in completely randomized design, you don't really take into account lurking variables or anything like that, and you just compare at the end. And why do you think? What's the importance of using a simple random sample at the very beginning, like a random number generator? Why is that? Yeah, you won't have. It does the best at eliminating bias, unless you are intentionally trying to eliminate or bias in very specific areas. A simple random sample does a good job because we came up with some lurking variables in the folic acid study, which things like genetics or other things that might compare or might affect the birth defect rates. But if you use a simple random sample, then there's a high likelihood that people from all the different categories are going to end up in both groups. That's why random sampling is nice. So anyways, that's the idea. And so here, the idea is just the ASRS, simple random sample, I would say it does the best at eliminating bias. So that's why we always use random sampling. Now, it may be, though, that you actually want to take those lurking variables into effect. Like maybe you think, maybe you have some reason to believe that folic acid might be effective among some people and less effective among others, or you just want to see how it behaves in different subgroups. So then that's what's called a randomized block design. So what you do is you take those women, and let's say that you give them a survey or medical history or something, and you find that some subset of them have family history of genetic defects, right? And so then maybe you find in your study 300 that have a family history. Okay, and then maybe the others, say 4,200. I'm making this up, but let's say that was without history. Okay, so what you're doing is you're splitting your population up into what we call blocks, and then the nice thing is you can split as many levels as you need to. I mean, unless you run out of people. But then maybe you also think that age is a factor, so you might split it into 35 plus or 34 and younger, and you could do that here too. In the 34 and younger. So whatever, let's just say there was maybe 100 of these and 200 of these or something, and then maybe there's 1,000 of these and 3,200. The numbers aren't that important, but you get the idea, right? So then what you've actually done is you've created 4 blocks now. So what we're trying to do is we're just trying to get more specific information from those subgroups. Then you would go, at that point, that's when you would do your split between folic acid and placebo. And you do it at every single, folic acid, placebo, you do it at every single level. Okay. And you do, again, you still use a simple random sample at the step where you're actually splitting people into groups. So you still have that randomness in there that also continues to sort of eliminate or work against any bias that might be introduced with other variables that aren't age or family history. So you're still introducing that random sample, and because you just split everybody evenly. So you'd split, this would be like a 50 and 50 split. This one would be like 100 and 100. So you'd still split your people evenly. So now the advantage of doing it that way then is because what you can do is now you can come back and you can compare within the 4 blocks, right? And then you have some really fine information. And then you can also, at that point, you can come back and you can compare between the split of your first variable, right? And then you can also come back and you can do an overall population comparison. So it allows you to make comparisons at multiple levels to see what types of information you can find. You know, how does folic acid interact with these other variables? And that would be able to help you really see that. Does that make sense? Because you might find that folic acid is very effective in some groups and may be completely useless in other groups, and you wouldn't know that if you didn't split them apart in a randomized block design. So, yeah? Does that make sense? Okay. Any questions about that? I think I might have mentioned randomized blocks and completely randomized designs in one of those quizzes. I can't remember. I feel like I did, though. All right. So then, what I want to talk about today, actually, did I ever start this? I did. Sweet. Is now that you have, once you get your data, so the first section was all about, Module 1 was basically all about, here's the big picture statistics, and in the big picture statistics, somehow you have to get data, so there's lots of different types of studies you can use to get data. But you got to get some data somehow. You can have observational studies or experiments. Simple random sampling is probably the gold standard for actually picking who participates. But now you went out, say you have your study, now you've collected your data, and so we want to talk about, okay, so what do you do with your data once you get it all compiled? So first off, just a reminder, there's different types of data, right? So in this one, this might be some data you collect with Boston Marathon racers or some other race. There's qualitative, there's discrete, and there's continuous. So which one of these would be qualitative? What do you think? This would also be known as categorical? Yeah, gender is probably that. Entrant number is probably close to a categorical variable. It's a pretty useless variable. So then, what about discrete? What's discrete? Place of finish is definitely discrete. And then the continuous ones are what? Yeah, their time and their age. They're actually both measures of time, so we can treat them as continuous, right? So we have 3 types of data. And then depending on the type of data that you want to analyze, like you would analyze time and age differently than you would analyze gender. Like you couldn't use the same types of graphs or summaries because they're just different type of data. So typically our first step once we have our data is we want to organize it. And then organizing the data, we typically split that into 2 categories. So for graphical summaries, these are things like tables, charts, and any sort of like graphs. Okay, so that's where you're taking your data and you're just trying to compile it into like maybe a table to simplify it, or maybe you have some graphs that describe the data really well. These are typically your first step, is to summarize your data into tables and then maybe make some charts or graphs that describe them. Numerical summaries typically come after that. Numerical summaries, these are values which summarize a data set. Okay, so it's like they're numbers that you can give me that take a lot of data and simplify it down to some summary information. So like if I have a whole bunch of data about like how many hours per week you guys work, okay, well I could just show you everybody's response in a big table, or I could tell you what?
Like the mode.
Yeah, I can tell you like the median or the mode or the average. So things like that, things like the mean or the average, like you said, the median, the mode. Those are all examples of numerical summaries because they take a whole lot of numbers and they condense them down to one number that you're going to give me that means something. So, anyways, first we'll talk about some graphical summaries. Then we'll move on to numerical summaries in the second part of the module. All right. And then we'll actually do some calculations eventually. So, all right. So, typically speaking, if you have different type of data, the differences start at the graphs because you just can't display the information the same way when they're different types of data. So, qualitative data you may use like tables, but qualitative data most likely you'll see things like bar charts or pie charts or pie graphs or whatever you call them. Okay. Bar charts and pie charts are nice because like pie charts help you see what chunk of a population a certain group takes up. Bar charts really help you see, which groups have a lot of individuals and which groups don't. I'm going to make some of all of these, but you are probably pretty familiar with these, I'm guessing. So then on quantitative data side, tables, of course, will work. Typically with quantitative data, though, we'll stick with what we call histograms. But there are, we'll also, in this class, we'll look at scatter plots. Scatter plots are appropriate when you're trying to compare two quantitative variables. So we'll look at those. Histograms, histograms are used when we'll do one variable. And those are the main types of graphs that we're going to work with in this class. There's other types, obviously, but we're just not going to get into every single type of possible data. Like we're not going to deal at all with like data that's recorded over time. So there's a whole field of, is that me? Okay. There's a whole field of statistics called like time series analysis where that's what they do. They look at data over time, but we're not going to get into that stuff. All right. Okay, so we'll just go through some quick examples here. I don't expect this to be a very complicated portion of the content. I have faith that all of you guys can make tables and graphs. So this is a pretty simple example. You got 40 students, 13 is Democrats, 18 Republicans, 9 is other. A frequency distribution, or sometimes called a frequency table. All you do, this is for qualitative data, is you just look for, or you just make a little table, and this is like, you list the different possible, Democrats, Republicans, other, and then it's called a frequency distribution because you're literally just recording the frequency, 13, 18, 9. So, because in reality, this is not actually what your data would look like. Your data would look like what? It would just be a whole bunch of different responses. So, it would just look like, or something like that, right? So the data itself, you wouldn't want to really look at the table with all like the D's and R's and O's in them or something like that. That would be a pain to try to figure out what's going on. So you just summarize them into like frequency distribution. That pretty quickly tells you, who has the most, who has the least, so on. Yeah? Now, sometimes the frequency is not the most informative thing to tell you. So like, for example, if I just came to you and I said, hey, I took a survey and 13 people in my sample said they were Democrats. So what does that mean to you if that's all I tell you? It doesn't mean much because what do you not know?
I don't know how many.
Yeah, because it's like, did you sample like 14 people or did you sample like 100 people? Because 13 means means something way different in those two scenarios. And so rather than reporting the counts, the frequency, we'll report the relative frequency. And relative frequency is just another way to say like percent or proportion. Like how often does it happen relative to the sample size? So in our case, we had, it was 13, 18, and 9. What we want to do is we just want to convert those into proportions or percentages by dividing them. Okay, so like, what is 13 divided by 40? Anybody got a calculator on them? They can plug that in real quick. 0.325? Yeah. Okay, so that would be the relative frequency. What's 18 out of 40? 0.45? Okay, and then the last one has to be what, 0.225? Yeah. Okay, so then the relative frequency distribution, it looks exactly like the frequency distribution, but of course, well, rather than recording the frequency, we would just record the proportion. We usually, you could convert these into percentages if you wanted to, right? Because 0.325, what is that? That's, 32.5%. This is 45%. This is 22.5%, right? So you could report that table in percentages if you wanted to. That makes a lot of sense to people, but we'll typically stick to proportions just because if you're going to operate with percentages, you got to turn them into decimals anyways, right? And so we'll just stick with a proportional form, like the decimal form. So, yeah? All right. So I am very confident that you all can make frequency and relative frequency tables. Those are plenty informative, but they're not very pretty. And so, people just find ways to take those two charts and turn them into a much nicer diagram. So pie charts would be dealing with the relative frequency distribution because you have, the nice thing is when you've already done the frequencies, then they're basically telling you what percentage of the pie to take up. So like technically you could turn these into degrees, right? So like a pie is 360 degrees and then you just take the percentage times that to give you pretty much, you could do it by degree and then you could get your compass out. But is it a compass or a protractor? Protractor. I don't even remember. Protractor. The compass is the one you make circles with. Yeah, the protractor measures things. Yeah, it shows how often I use one. Because nobody has a protractor. So we'll just draw it and it'll be good enough. So 33%, that's like basically a third. So that would be your Democrats. And then your Republicans is 45%. That's a little less than half. And then that would be other here. So boom. Yeah? And then you add colors if you want and make them 3D or something if you want. I don't know if I can make a 3D chart. Nope, I can't. Whatever. You get the point. Okay. So I am sure you've all encountered pie charts at some point in your life. Yes? Cool. I'm just going to keep moving then. The bar chart usually uses the frequency data though. So it'll take the frequency, and usually what's normally at the x-axis, if you're doing qualitative data, you just make a bar for each category. And so just be like, Democrat, Republican, other. And then over here, your y-axis is the frequencies. So ours go up to, looks like 18 is our biggest, so we'll go up to 20. And so then you just make a bar as high as the frequency. But the bars are separate, and that's important, kind of. So, Democrats at 13, Republicans were up here at 18, and then other was down at 9. Okay, so that's a bar chart. Notice it's qualitative data as a bar chart, and the bars don't touch, and that actually matters because in qualitative data, does it actually matter which order you put your categories in? It really doesn't. You could put them in order of size if you want to, or you could put them in reverse order of size, or you could put them in random order. It doesn't really matter. And so that's why the bars don't touch. Because there's no reason that you had to put Democrats first there. You could have put other first or Republicans first, and so on and so forth. Okay? So in bar chart, the bars don't touch. All right. Phil, you can make a bar chart? I also think you can make a bar chart. All right. So those are the two main types for qualitative data. If you start getting into quantitative data, then you have to just, you can't make a category for every possible, sometimes you can make a category for every possible number. It's not always the case. So like here's some quantitative data. This happens to be what type of variable? Number of TVs. Is that discrete or continuous? Yeah, so that's a discrete or a discrete value. And so when you're looking at discrete data, you usually can, a lot of times you can use single value grouping. In other words, we'll give every single number its own category on the table. So then, dang it, I need to remember to keep this. I'm going to copy that table. Just move up here. All right, so then we can make a frequency distribution now. So, it'd be like number of TVs in one category, and then frequency over here. And so all the options are these, right? That's it. And then you're just reporting how often each one happens. So it'd be like, you go through, well, how many people had no TVs? Was it just one? All right, then you go through, how many households have one TV? So you just go through, and maybe you can count, I'll count, we'll see what comes up. 16? Okay. And then you go through how many had two. Maybe you could just pick a number and count them and tell me how many you get. And we'll see what we come up with. How many were two? Yeah. 14? People seeing 14? Okay, we'll be able to check our math at the end pretty easily. How about 3? 12. Is it 12? Yeah. 12? Okay, how many have 4 TVs? Is it 3? How about 5? Is it 2? How about 6? Is it 2?
You said 3 and then wrote 4 for 4 TVs.
Oh, is it 3?
Yeah.
This one's not 4, it's 3. Oh. This one was 3. Okay, does that add up? Now we can just check. Does that add up? What are those add up to? That's 30, 31, 43, 46, 48, 50. Perfect. Okay, so the frequencies obviously should add up to the number of data. So then that looks fine. You could turn them into relative frequencies, but we're not even going to worry about that right now. Obviously, so if you wanted to turn it into relative frequencies, you just take each number and divide it by 50 in this case. Or was it 40? I think it's 50. And then that would get you your percentages. Okay? So that works really nicely when your data is discrete. You probably could use single value grouping as long as there's not that many options. But then when the data gets a little more spread out, or maybe it's more like continuous data. So if we're talking about number of days, that's technically discrete, but because of the way the data is spread out, it's really more like a continuous random variable. And so when you have continuous random variables, if I want to turn these into a table like the last one, what are we going to have to do? Because I can't put a category for every single number. Yeah, we're going to lump them into groups. So we're going to pick what we call classes or bins or widths. And so we're just going to split this range up. And so if you look here, our data goes from where to where? Like 10 to 99, So it's a range of about a 0 to 100 or somewhere in that range, and 10 to 100. And so what you want to do is you just want to split the range. And typically we try to go like 5 to 8 groups. Like splitting it into 10 groups is kind of getting pretty big, but somewhere in between, we can say 5 to 10. So you just want to look at the size of the range and then split it into equal sized groups that maybe end up give you like 5 to 10 categories. So if we're going if we think of this as like 0 to 100, we could just do it by 20s, right? So then what we could do is we take our data, and again, I think I didn't keep this, so let me grab the table. Maybe. Oh, what did I do? Oh no, I didn't do anything. All right, so then we could maybe think about sizes of 20. And so maybe we'll go from like 0 to 19. Our next one will pick up at 20. Our next one would pick up at 40. Then it'd pick up at 60. then it'd pick up at 80. And that would get us like our 4 bins that are equal, or our 5 bins that are equal size. And then we would record the frequencies, the ones that just fell in there. So then we're looking for, okay, so how many were between 0 and 19? So that's zeros or teens. It was just one of them, right? So just one of those. How about in the 20s or 30s? How many were in the 20s or 30s? I see 3 at least. I see 3. I see 38, right? 36 was down here, and there's another one. 39, right? So there's 3 in there, in the 20s and 30s. Then you go through, and you're looking 40s and 50s, right? So there's like 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that all? 9 in the 40s and 50s. Okay. Then you go through like 60s and 70s. So then that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Any other ones I missed? Am I making it better or worse? I don't know if that's better or worse. Okay, yes. Both. And then 80s and 90s, so that'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Something like that. Yeah? Okay. So with continuous data, you just split into those groups. They're both kind of like, I mean, both of the tables, they're both frequency distributions, so, you know, they're kind of similar. And then like with the, do you guys have questions about it? I feel pretty confident you guys can make these as well. And then what we do typically with these is just like frequency distributions were turned into bar charts. We do the same thing for quantitative data, but we call them histograms. And the reason they're a little bit different than bar charts is because if you look at this data, since it's quantitative data, the order of the categories kind of matters. Like you wouldn't really necessarily take these out of order. And so in a histogram, we run them up against each other. So like for the number of TVs, if you have a discrete random variable, you just give a bar to every possibility. Well, actually, normally what will happen is the bars would start at, you know, whatever the number was. You could do it the way I wrote it before, but it wouldn't really make much sense. So then, like, for 0 to 1, then we still do the frequencies. So what did the TV data look like? It went up to, like, 14, 16 at its max. So then maybe go 5, 10. All right. So then for 0, how many people had 0 TVs? I don't remember. Was it? There was 1. Okay. So it was like there was 1 person with 0 TVs, so they would get a bar there. And then the next bar, it jumped up to 16, didn't it? Well, come on, connect. But the thing about a histogram is that the bars are going to touch. Okay, and then, so that one was up to 16. What did the next one drop down to? So after 16, it dropped down to what? I don't remember. 14? Yeah, so it went down to 14, and then it went down to 12, and then it dropped down, I think, yeah, to 3, then 2, then 2, right? So it was then 3, then 2, then 2. You know, and you could color the bars in if you really want. You don't have to. But you get the idea, okay? So the bars touch. Now, the thing about histograms is that histograms start to show us what we call the shape of a data set. And so, like, if you look at the number of TVs, where are most of the households kind of piled up? Yeah, they're all kind of piled up down here, and then it sort of tapers off as you go towards higher numbers. So you can kind of think, you know, this almost has like a little shape to it. And we'll see something different on the ones with the financial or the investment days as well. Okay, and then we'll talk a little bit about shape because it matters. So like if we look at this one right here, our days to maturation. So that one we split up on the 20s. Okay. So here's 0, you know, here's 20, 40, 60, 80, 100. And then the bars went from what? Up to about 16, so same kind of scale as before. 5, 10, 15, say. And then it was one, so there's one person in this first category, and then didn't it jump up to 3? Yeah? 3 there. Then there was 9 investments, and then it jumped up to 16, so the next bar jumped up to 9. And then we jumped all the way up to 16. And then the last one was 10 days in that last category. So that'd be about like right here, right? Like something like that. Yeah. And now what's the difference in the shape of this one versus the last one? Yeah, so in the last one, most people were piled kind of down at lower numbers, and you had a few people in higher numbers. But here, it was sort of the opposite. There was not so many investment down at the lower numbers, but there was a lot of the investments piled up at the higher numbers of days. Okay. So what we're getting at here is the shape of the distribution, or the data set. Okay. All right. So when we're talking about that distribution of data, what does it mean to distribute something? It means it's like how it's spread out, right? A distribution is just how you spread it about wherever it's going. And so the distribution of data, it's how data are spread over their range. Okay. Because the range doesn't necessarily tell you that much. So like if you look at let's say that you look at the GPA distribution of 2 different classes, right? So all the classes go from like 0 to 4.0, okay? And then you look at another class, they're also from 0 to 4.0, right? Well, let's say that this class looks like that, and let's say that this class looks like that. Okay. Well, which class would you rather be in? Say they're like 2 sections of the same class. Which one do you think? Class 1 or class 2? My class 1 is not a very good drawing. That's not how I meant to draw it. Those ones look too similar. I was going to make it more like, didn't translate. I was going to make it more like that. Right? So which class would you rather be in? You're going to rather be in class 2, because in class 2, where are the majority of students? They're up at the higher end, and there's a few students that taper over here. Now, in class 1, people are kind of more condensed. It's not quite as spread out, but the center of it is lower, and so we want to have graphs and numerical summaries that help us understand what the distribution of a data set is like. Am I dealing with that kind of data set? Or am I dealing with that kind of data set? Or am I dealing with something else? Okay. And so there's 3 main characteristics about the distribution of data. What we care about is the center, the spread of it, okay, and we care about the shape. So where's the center of the data set? How spread out is it? And what's the shape of it? And so the center and the spread, we're going to look at a lot of numerical summaries that deal specifically with these. Though you can kind of see it from the graph. The graph kind of shows you where the center is and how it's spread out. But the shape, this is really only something that you can get from, it's supposed to be a P, not a B, from graphs. Okay. And so when you're analyzing a data set, you should never ever skip the graphing stage because graphs can tell you a lot of information about a data set. They help you see the shape. They help you try to find outliers. Right? There's a lot of things that a graph can show you that just numbers and just the data set itself can't. That's the idea. All right. So we were talking about the shape. one main thing that we look for when we're looking at the shapes of distributions is we're looking for symmetry and skewness. And so sometimes what you'll have is you'll have data that has nice symmetrical distributions. And one of the main ones that you probably have encountered or seen, and one that we work a lot with in statistics, is what's called a bell-shaped or normal distribution. So in a bell-shaped or normal distribution, it's very symmetrical, and then typically it's symmetrical around its center, right? And so in the center might be like the mean or the average or something like that. And in symmetrical normal distribution, most of the observations are kind of piled up right around the average, like in the middle. Like most of us are all piled up right here around average. There's a few people that you'll see that are below average. There's a few people that might be extremely above average, but there's not that many of them. Okay. So we're talking about quantitative data, single variables. So what do you think might be some examples of data that might have a symmetrical distribution, where almost all of us are kind of piled up around average? Some are exceptionally on the high end, some exceptionally on the low end. Yeah, so height is a great example. So you'd want to restrict yourself to like a specific population. So maybe like adult U.S. males or something, right? The height of adult U.S. males has a very bell-shaped normal distribution because almost all of us are going to be piled up right here around the average. I don't know what it is, 5'10", 5'9", or something like that. Most of us are going to be within a few inches of that. Occasionally, you'll see a few people that are really short. You'll see a few people that are super tall. They happen, but not that often. And they happen kind of equally on both sides of the distribution. You have about as many really, really tall people as you have really, really short people. Okay, that's a key characteristic of a bell shape because it's symmetric. What else? Can you think of anything else that might have a bell shape or normal distribution? Income. What do you think about income? Do you think income is symmetric? Yeah, so probably depends on who you're measuring the income of. But income is actually a good example of, well, I'll just switch these slides because it's probably an example of a distribution that has what we call skewness in it. In a skewed right distribution, then what happens is there's some dissymmetry to the distribution in the sense that you only see the tail of the distribution. So this is what we would call the tail of the distribution for obvious reasons because it looks like a tail. The tail of the distribution, it stretches to the right. Okay? And so it's like most people are down at the bottom of the distribution, right? And then only a few individuals are ever found at the outlying ends of the other side. Okay? So examples, the income typically actually would fall in a shape something like this. So if you look at the income of adults in the U.S., it's typically going to have a skewed right distribution because where are most of us at? Yeah, I mean, most of us are probably, and we're talking, I mean, the scale is ridiculous when we talk about income, but like most of us are probably going to fall somewhere in the like zero to $500,000 a year, right? That explains like most Americans. Now, of course, are there a few out at the ends that earn way more than that? Certainly, but most people are kind of at the bottom or somewhere in that lower portion, right? What else might have a skewed right distribution where most people are at the bottom and some people are on the high end? Any ideas? What else might be shaped like that?
Children.
Yeah, so if you look at, typically that's true. If you look at number of children per household, like in the U.S., where are most households? Somewhere between like 0 to 4, 0 to 5 kids. Almost all households are somewhere in that range. Are there households that have like 8 kids, 10 kids, 15 kids? It happens, but they're not as common.
I want to say households, but
What's that?
I feel like one family has like 15 kids.
What's that? The house? Were you saying another one, or are you talking about that one?
No, it's just for the
Oh, okay. All right. Anything else? What else might have a skewed right distribution?
The number of cars a person has.
Yeah, like number of registered vehicles would be definitely probably skewed to the right. You know, most people probably have between 0 to 3, 0 to 4 vehicles. I don't know. And then, like, are there people with like 20 or 100? Like, yeah, it happens. They exist. There's not many of them. Anything else? No, yeah, it's anything that most people would have a few of and some people would have a lot of, you know, like pets, cats, right? Dogs. Most people have a normal amount of them and some people have a lot of them. Okay, so then what about any more here for symmetrical? Or if you can be skewed right, then you could probably be skewed left, right? So it's where most of your data is piled up at the higher end, but the tail gets stretched off to the left. So you could also have things that have a skewed left distribution. Anybody imagine a number that you could record about, say, people, where most people would be at the high end and a few people would be at the low end? Age of what? Like just age of Americans?
Wouldn't that be like more like about?
That's probably going to be skewed to the right, because most people, and that's going to be a goofy one. I have no idea, actually. I'm not sure. Because it'd probably be almost uniform across a lot of age groups, and then it would drop off and be pretty skewed out towards the higher ages. So, I don't know about that one. What else? But age of a certain type of person might qualify here. Excuse me.
Of a house owner or something.
Maybe age at first, like when you first bought a house. Maybe that one could be a little more normal or skewed the other. I'm not sure. Skewed the other way. Yeah.
Would you say like age of politicians since there's like age requirement?
I was thinking something like that. So like anything that typically doesn't happen until you get older. So like becoming like a senator or something. Most people are older when they become senators because they have some other political career. Do you have some really young senators? It happens. So I think that would be like a decent example. So if you look at like age of senators, I think that's true. What's another thing that you don't usually do until you're old?
Nursing home.
Yeah, if you look at like age of like you said, like assisted living residents.
Retirement.
Yeah, exactly. You know, age of retirement. Yeah, so it's just the opposite. Most of us will retire somewhere up in our higher years. You know, 50s, 60s, 70s, or whatever, onward. Some people retire early. Doesn't happen that often, but some people do. So yeah, that'll be skewed left. Any more for, we don't have many here though.
GPAs.
What do you think GPAs look like?
I think like 5 or 3.
No.
maybe like substance use.
Isn't average GPA like 2.5? So that's like right in the middle.
I don't know what the average GPA is, honestly. What were you saying though?
Like substance use.
Like what?
Like drugs.
Well, okay, so remember that we're measuring quantitative variables, so it has to be a number value that you have to be looking at. So it has to be a numerical value that you're measuring about people.
Our
There's actually not that many that occur this way, yeah.
I was just gonna say that the average GPA, like average for high school, is like 3.3.
Yeah, I think GPAs actually tend to look, especially like if you're looking at active students, I think GPAs actually tend to look more skewed to the left. There might be a little bigger tail on the right side, but you know, they tend to look like. I mean, you might have like a the skew might not be as extreme, but I would think it's probably something like slightly skewed. Because we just don't, if people have super low GPAs, they're just not in school typically anymore. So you don't see as many super low GPAs among active students. They happen. It looks something like that. So I think actually GPAs would be, and I know the GPAs for students in my classes look like that. At least the ones that are still in the class at the end. So, all right. Man, it's symmetrical. Anything else? Come up with one more and then we can leave.
The weight of the goat.
What do you think?
If you categorize it like times,
If you look at weights of adults, I think you're probably going to end up with some probably skewed right. Because there's sort of like a minimum weight of an adult, right? Like say you're looking at a minimum weight of adult males, for example, right? There's like there's sort of a bottom, you can't go below, like you're not going to find many males under like 100 pounds, right? There's just not many. And then between like 100 to like 300, you're going to find most males, right? Anywhere in that range. But I mean, are there males that weigh 400, 500 pounds? Like they exist, there's just not many of them. So they actually probably have a little bit more of a skewed right distribution, I think. Something like that. That one's harder because this one, the funny thing is we use the normal distribution more than any other distribution in statistics, but not a lot of things occur that way naturally. Yeah. Sorry, go ahead.
I think it seems to me like you could put anything on there that you do daily, like how many meals a day you eat, or how many times people brush their teeth a day.
How many times people brush their teeth? That would be weird because there's not that many options that people would claim. It'd be like 0, 1, 2, maybe 3 or 4. I don't know how many people.
In my head, I'm thinking like some people might brush their teeth 10 times a day, and you have
or like the
some that
OCD
are-
people who wash their hands constantly.
See, I think that's going to get into skewedness because you look at most people, how many times do they wash? Most people brush their teeth between probably 0 to 2 times. Hopefully 1 to 2 times, but there's probably people out there that don't brush their teeth, whatever. But there's going to be almost all of us going to be down there. But are there people that probably do it 5, 10, 20 times a day? Probably.
Like what time people, like if the center was noon, what time people eat lunch or something like that?
It could be like what time people eat lunch at an office or something. That might have a normal distribution, something like that. It's really not common. That's the thing. There really are not a lot of naturally occurring normal distributions. And when you do see them, a lot of times they're imposed. So if you look at SAT or ACT scores, or if you look at IQ scores, things like that, standardized tests, they sort of manufacture them. They actually try to build the test to produce normal distributions. They do it on purpose. So they design them in a way that makes normal distributions out of the test takers. And it's just that there aren't very many things that just naturally take on normal distributions. It just doesn't happen that often. But it's such an important distribution to statistics because you can force a lot of data into normal distributions. Even if they don't naturally occur as normal distributions, you can make them look like normal distributions by doing certain things, like averaging them or something like that. And we'll study a lot about that phenomena in this class. But the point is that there's different shapes of distributions, and we're going to look how that shape can affect center and spread. That's what we're going to start on tomorrow. So that's all I got. Good timing.